honorable chairs, distinguished colleagues, it's my pleasure to meet you again. Now I would like to give a brief introduction to my research titled Average Capacity Analysis and Power Allocation for Data Gathering Wireless Sensor Networks. Now let me guide you through the structure of my presentation. I will begin with the background and motivation, followed by the system model. And next, we will delve into the core of this presentation, average capacity analysis and cooperative power allocation. Finally, I will conduct simulations and conclusion. Data gathering wireless sensor networks, DAWSNs, have emerged as crucial infrastructure in modern sensor systems, enabling the data collection of valuable information from remote or inaccessible environments. Their applications are diverse and span critical areas, including industrial automation and IoT, data collection using UAVs, and traffic data collection, among others. Applications utilizing the DAWSNs encounter challenges related to limited capacity and battery life. Thus, there is an urgent demand for providing both high capacity and low transmission. Aligning with the objective of 5G and the next generation 6G mobile communication technologies. However, achieving high capacity necessitates significant bandwidth, which considerably increases both power consumption and the cost of analog to digital converter ADCs. Specifically, the power consumption of ADCs scales with sampling rate fs and the QB power of 2, where QB is the number of quantization bits, to enhance the longevity of DAWSNs and expand their applicability. Deploying the low resolution ADCs with a smaller QB can effectively induce the power consumption and costs. As shown in the slide, high resolution ADCs has more channel capacity with high RF power consumption, and low resolution ADCs has lower channel capacity with slight power consumption. However, low resolution ADCs with power allocation bears a large number of capacity improvement with slight power allocation consumption. Thus, low resolution ADCs with power allocation PA make us effectively lower power and cost consumption while maintaining its capacity. To achieve this, we need to analyze the average capacity and designing a PA scheme. The non-linear channel model induced by low-resolution ADCs presents significant challenges for channel capacity analysis and power allocation design. This figure shows the non-linear mapping process of ADC. The traditional linear model for high-precision ADCs is no longer applicable. Now let's move on the system model. As shown in the figure, consider a many-to-one data gathering WSN, where k independent single antenna source nodes transmit data to a sink with n antennas, utilizing the same time frequency resources. Each sink antenna is connected to an RF chain equipped with ADCs to quantize the received signal. Following the Bascom decomposition, the non-linear model is transformed into a linear model, converting the quantization noise into additive Gaussian noise. Research has shown that this linear model also maintains a high level of accuracy. These parameters are shown in the slide. As I mentioned in my previous lecture, the channel model is crucial for WSN systems to capture both the small-scale fading and large-scale fading. We choose a model applicable to various DAWSN scenarios. The channel is modeled as shown in the slide, where G is flat fading channel matrix with unit power, and D means large-scale fading matrix. It equals to diagonals of beta 1 to beta k, where beta is the large-scale fading coefficient from the source node to the sink node, assumed constant during the transmission. After the system model is established, we will dive into the core of this presentation, average capacity analysis and cooperative power allocation. The average capacity can be achieved when SK follows a complex Gaussian distribution with zero mean as given in the slide. Compared with small-scale failing, the large-scale failing coefficients are assumed to be stationary in a period. This implies that the expectation with respect to H only considered to the fraction of G. The Monte Carlo simulations are time-consuming and not analytical expressions. So we want to eliminate this expectation. We are committed to deriving its tractable expression. We derive it using the replica method. The replica method is a powerful technique originally developed in statistical physics to study the complex systems, such as glasses and disordered materials. It involves introducing multiple replicas of a system, each presentation a different state of configuration. By average over the replicas, researchers can derive the properties like free energy and phase transitions. In the context of wireless networks, the replica method is used to analyze the average capacity of channels under various conditions, particularly in scenarios with noise and interference. By modeling the communication channels as statistical physics problem, it allows for a better understanding of how signal processing strategies can be optimized for performance. After some tedious but straightforward calculations, we can get the tractable average capacity expression as shown in the slide. The analytical expression allows channel capacity to be solved using a simple fixed point iterations. Obviously, the average capacity is a function with respect to the transmit power P. We attempt to optimize the average capacity by employing the suitable PA in source nodes. This problem is an optimization problem as shown in the slide. The first task is to eliminate the influence of the fixed point equation. As the solutions to the fixed point equations, the partial derivations of capacity with respect to MSE and SNR are equal to 0. Thus, the impact of perturbation of fixed point can be ignored. Next, following the general optimization approach, we can formulate the KKT conditions and formulate the optimization problem to the equivalent optimization problem. This is a simple problem. It can be solved using the standard water filling procedures. Combining the fixed point equations, we propose a CIWF algorithm summarized in algorithm 1. The CIWF presents the cooperative iterative water filling algorithm. It works in an iterative way to obtain the optimal power allocation and the corresponding fixed point equations. Since MSE and SNR depends on P, the step 2 in each iteration updates MSE and SNR using the newest P. The step 3 in each iteration updates P using the standard water filling procedure when iterations terminate. The algorithm will output the final obtained power allocation algorithm. Now we will move on to the simulations. In this section, we conduct simulations to validate the proposed analytical results and the performance of the CIWF algorithm. During the simulations, the source node number is set to 32 and the sink attendance number is set to 4. The conventional midpoint uniform quantizer is considered. In the left figure, we compare the analytical results with Monte Carlo simulations under uniform and CIWF-PA. Our curves merge together with the Monte Carlo simulations. Thus, the analytical result is accurate for a wide range of SNRs and different PA schemes. In the right figure, we validate the effectiveness of CIWF algorithm under different QB values using the uniform PA as a baseline. By implementation CIWF, we can achieve compensation for the loss caused by quantization. This figure illustrates the convergences of fixed point equation and CIWF algorithms. It's showing that only 3 to 5 times and 2 to 3 times iterations are sufficient for a fixed point iteration and CIWF convergence respectively. This means that through the cooperative PA, one can harvest a remarkable capacity gain and at a mild cost of computational complexity. The final section is the conclusion. This paper has derived the analytical exploration of average capacity by resolving the replica method and designed the CIWF PA scheme to enhance the capacity for DAWSNs, where Sync is configured with low-resolution ADCs. Numerical simulations verify its high accuracy and reveal its effectiveness of CIWF PA algorithm, which compensates for the capacity loss caused by low-resolution ADCs with relatively low power consumption. That's all. Thank you. Any questions?